In this video, we're going to be talking about how do we represent elements, passive elements, that's the resistor, inductor, and capacitor in phasor domain. We're going to use this parameter called Z. This parameter called Z to represent it. Z is defined, and this is simply a definition, so there's no proof. Is in phasor domain is defined as V over I. Since it's volt over amp, the unit for this is simply ohms. And this is referred to as impedance. Because of its definition, it looks a lot like resistors did, where the Ohm's law told us was R is equal to V over I. Here Z is equal to V over I. But this is much more powerful because you can also represent inductors, capacitors, and resistors with the same relationship, and more or less say always that V and I are related to each other with Z. So our job here is to see how the time domain values of those inductors get translated to the impedance for those inductors and capacitors and resistors. Let's start with an easy one. We're going to start with a resistor, and if I've got a resistor, so we're doing the resistor, and R is its value. So now if I come to the resistor, and let's say I say given that I have a current flowing through here, so if I have a current flowing here such that I of t is equal to Im cosine of omega t plus theta I, if that's the case, can you figure out what the voltage is? In time domain, yes, we have the Ohm's law, always applies. So V of t is going to be R times I of t. So in this case, that basically would be R Im cosine omega t plus theta I. Fair enough, pretty straightforward. So now we're going to take this thing to phasor domain. So we're going to phasor domain, and there are earlier videos that tells you how to take current and voltage into phasor domain. So I'm going to take it to phasor domain and going to go to a polar form. So if I do that, then I in the phasor domain would be the maximum e to the j theta I, because omega we know is the constant, we don't carry it. And then the v is going to be R I m e to the j theta I. Well, our definition was that Z is going to be equal to V over I, and if I do that, you can simply see this is going to be R I m e to the j theta I divided by I m e to the j theta I. And as you can see, this cancels this, and you're R. Therefore, for resistors in a phasor domain, Z is simply R. That was easy. Now let's see if we can do it the same thing for inductors. For inductors, which L represents, so let's say you've got an inductor, and let's say your inductor has a current that comes through, and your current is the same. I of t is equal to Im cosine omega t plus theta I. Great. So now the question would be, can you figure out what the voltage is across this? Sure, the voltage, this is supposed to be minus. Because this is passive, it's going to be plus minus in the direction of current. So sure, V of t, we know in an inductor is L di dt, which means I just take an L and multiply by derivative of that. You know, derivative of cosine is minus sine. So we've got minus L omega I m cosine of omega t plus, I'm sorry, this would be, it's the derivative, so it would be, actually sine. If from the work we had done earlier, you know that we have to take this to a cosine. Taking sine to a cosine, you got to subtract 90 from it. So V of t is actually minus L omega I m cosine of omega t plus theta I minus 90. Great. So now we got to take this into a phasor again, phasor domain, and we've done enough to know that I is going to be equal to Im e to the j theta I, and the voltage is going to be minus omega L I m e to the j theta I minus 90. Well, we know that now that we have V and I in the phasor domain, Z is simply V over I. Great. So if I divide these two together, what I'm going to end up with is minus, actually this is minus omega L I m e to the j theta I e to the minus j 90. And the bottom is going to be Im e to the j theta I. Well, obviously this cancels this piece, and we'll end up with Z equal to V over I equal to minus plus j omega L, because this thing is simply minus j. So you convert it to rectangles. So for an inductor, Z is equal to j omega L. Beautiful. And the last thing, following the same exact process, what we can do is we can find out if capacitor we can do the same thing for capacitor. Sure enough, we can do that for capacitors, because capacitors, we're going to do it a little bit differently. So if this is my capacitor, and let's say now this time I'm going to assume that I have a voltage across this V of t equal to Vm cosine of omega t plus the theta v. So if that is the case, then I've got I can find out what the current is through here, and we know that current through a capacitor is C dV dt. And of course, from the earliest, we know that derivative of cosine is minus sine. So we're going to end up with minus Vm C minus C Vm omega sine of omega t plus theta v. And we know that in order to go to a phasor domain, it has to be a cosine form. So we've got minus C omega Vm cosine of omega t plus theta v minus 90. Following the same process, we know that Z is defined to be V over I. So we'll take the V divided by the I. First we got to take them to phasor domain. Sorry about that. So if you take these to a phasor domain, the voltage will be just simply Vm e to the j theta v, and I is equal to minus Cw Vm e to the j theta minus 90. Great. So now when we divide those together, V is going to be Vm, and the bottom is going to be minus C omega Vm e to the j theta e to the minus j 90. I'm going to separate those so it's easier to see. So this cancels that, this cancels that, and we know this as from the earlier work we did. If you go to a rectangular form, this is simply minus j. So now we've got 1 over j omega c. All right, so now to summarize everything we've done, we have been able to say that R, when you go to a phasor domain, Z is equal to R. And then when you have an L in the phasor domain, the Z for an inductor is equal to j omega L. Of course, omega is the frequency, radial frequency for this. And C, the Z for that is it's 1 over j omega c. So here we go. Now at the earlier video, we talked about how to take sources from one domain to the other. Now we know how to take the elements, now the passive elements there. Now we can take any circuit we were given and transform them into a phasor domain. In future videos, we're going to use the knowledge we've gained here to take a circuit from a time domain to a phasor domain, do the analysis on it, and get whatever current or voltage we are looking for. That brings us to the end of this particular video.